Hi guys, it's Daniel here, and today we're going to do part one of a two-part video on Euler's theorem. In this part, we'll just be teaching you what Euler's theorem is, and in the second part, we'll be using Euler's theorem to solve this problem that we have. So first off, what is Euler's theorem? Well, Euler's theorem is kind of like a generalization of Fermat's little theorem that I did two videos on in previous weeks. And instead of a to the power of some prime number p congruent to 1 mod p, we have a generalized mod n. So it states that a to the power of the totient function of n, did I pronounce that right? I don't know, totient function of n is congruent to 1 mod n. So first of all, what is this totient function? Looks kind of like phi of n, but it's a function. Well, this basically just counts the number of numbers that are below n, that are relatively prime to n. For example, the totient function of 6. Well, first of all, let's list all the numbers that are under 6. 1, 2, 3, 4, 5. And which ones are relatively prime? Well, 1 is relatively prime to all numbers, so that's 1. And 5 is also relatively prime. So this is equal to 2. So, if we have, let's first delete this. Delete this thing. Alright. So, we have a to the power of the totient function of n, which is the number of numbers under n which are relatively prime to n, is congruent to 1 mod n. And I'll go over how to find the totient function of n for any n, but for now, let's just pretend that you can find the totient function of n. So we have that a to the power of totient function of n congruent to 1 mod n. Well, does that agree with Fermat's little theorem? So if we have the totient function of a prime number p, then, well, all the numbers that are under p are congruent to p. Are relatively prime to p, except for 1. So this is just equal to p minus 1. So by Euler's theorem, a of the totient function of p is equal to a to the p minus 1th power, congruent to 1 mod n, 1 mod p this time, and that agrees with Fermat's little theorem. So at least we know that there isn't any contradiction here. So now that we've confirmed that this is indeed a generalization of Fermat's little theorem, let's get on with finding the value of the totient function of n for any n. So first off, we know that n can be separated into its prime factors, which are, let's say, the first prime factor is p1, and then this is to the power of e1 times p2 to the power of e2, and then so on. For example, if n was 12, then this would equal 2 squared times 3. So we take these p1s, e1s, and we can use them to find the totient function of n. So the formula states that the totient function of n is equal to n times 1 minus 1 over p1 times 1 minus 1 over p2, and so on, until you've gone through all the prime factors of n. For example, if we have the totient function of 6, then we can see that 6 equals 2 times 3, so 2 and 3 are both prime factors of this. And by our formula, we calculate the totient function of n is 6 times 1 minus 1 over 2 times 1 minus 1 over 3. See, this is 1/2, this is 2/3, 6 times 1/2 times 2/3, these two cancel out. So 6 times 1/3, which is equal to 2. And we confirmed that the totient function of 6 is equal to 2 in like a few minutes ago. So this formula we just confirmed is correct. And I won't prove this because it's just going to take too much time for this video. So I think we are done explaining. Oh yes, one last thing. A and n are relatively prime because if A isn't relatively prime to n, then obviously it can't be 1 mod n. So in the next video, we will be solving this problem using Euler's theorem. And before you watch the next video, I suggest you try to solve this on your own.
Hey guys, Long here. Back with another math video. Last week Daniel did Fermat's little theorem, and last week I did some AMGM. So I'm going to build on some AMGM. So we have your problem. It's from USAMO 2011, number 1. So it's a USAMO problem. So it's definitely not easy. So let's just jump right into it. So if you want to try to solve it, pause the video and let's go. So let's take a look at this first, because this looks rather interesting. So you know what? Let's just expand this condition. So a squared plus b squared plus c squared plus a squared plus b squared plus c squared. Sorry, lag. It is horrendous. By the way, happy Halloween. I hope you guys got a ton of candy and stuff like that, because you know I love candy. So let's see. So you expand into that. So this thing is this thing. So this thing is this thing. So